In this video, we're going to show you how to calculate the online real-time cost to treat a source like this and show you what value that can give to operators and managers. The first thing we need to do is work out how much chemical we're using. We have here the coagulant. Now the coagulant is probably the biggest proportion of the chemical costs. So on this plant we're lucky in that we meter the coagulant, so in real time we know exactly how much coagulant we're using. Now because we know the supply cost of the coagulant, we can work out basically the real-time cost of using the coagulant. Here we have the line. Now the line on this plant is a little bit trickier. We're using a dry feeder to dose the product with a wetting tank. So we're not really metering the exact amount of lime that's going in. So the way we can calculate the lime dose and therefore the lime cost is based on feeder speed. Now to do that we need a feeder calibration. So we can relate the speed to the amount of mass delivered. And we know the supply cost of the hydrated lime. So that's our online cost of lime. The next chemical is CO2, carbon dioxide. For CO2, it's quite easy. We've got a gas flow meter here measuring kgs an hour. We know the supply cost of the CO2, so therefore we can work out a real-time cost. The next chemical is polyelectrolyte. Now, on this plant, we're lucky again that we have metering on the polyelectrolyte dose flow. We know the batch strength, and we know how many kilograms are in the per meter cubed of batch that we make up. We know how much of that batch strength we're dosing, and we know the supply cost of the powder poly. So again, we can work out a real-time poly dose cost. This is the chlorine. Now the chlorine isn't metered directly, but we have a V-notch, which is a percent position, and we have a rotameter, which gives us an indication of the gas flow. So we do a calibration between the V-notch position and the gas flow. So then for any V-notch percentage position, we know how much gas has been delivered. We know the supply cost of the chlorine, so we can work out a real-time cost. The next thing we have to calculate is sludge disposal. Now on most plants, sludge treatment is a batch process, so calculating an online cost is quite challenging, so we have to be a little bit smart about this. Now on this plant, we have a centrifuge which is operating periodically, produces the dried solids of 21 to 22%. It's collected in these sludge bins, and then it's taken to landfill. Now we know the charge for the landfill. We also know how much it costs to transport these skips. So what we need to do is work out a real-time sludge production. So we do that by using raw water flow, raw water turbidity, dissolved organic measurement, and measuring the amount of coagulant that we use. All of those can be used to calculate an online sludge production. And then with the disposal costs, we can convert that into a real-time online cost. We also need to know the power used on site to work out an online treatment cost. So on this site we've got some pretty big power users. There's a big pump station here to move the treated water into the system, but it's all metered. So we have power metering. We know the spot price of the power, so we can work out a real-time cost of power.
Now that we've explained how online treatment costs for a source like this can be calculated, we'll show you a few examples of how that can be used in infrastructure data to provide operational and management insight. First of all, let's look at this from an operations perspective. This dashboard shows the inlet water quality and the actual and predicted cost to treat. As would be expected, the cost to produce water increases when the raw water quality deteriorates. However, it's not immediately obvious what is driving the cost increase. We can drill into the data and plot cost against all sorts of variables to determine what has the most impact on operational cost. In this example, it's the amount of dissolved organics, and in particular the type of dissolved organics present, which is really impacting on our operating cost. This is a great way to increase operator understanding of the process, and indeed to allow them to fully grasp the impacts of increasing chemical doses. With the predicted cost, we can also run a cost sentinel feature. This is a comparison of the actual cost versus the predicted cost, and we can alert based on errors. So if there's a deviation, the suggestion is that it's an off-normal situation. Put simply, there's something going wrong on the plant that warrants investigation. Now we're looking at a period of 3 months here. We can also very quickly change the time periods and zoom in. Let's just have a look at 3 days, for example, here. We can have a look at a week, and we can see if these patterns are changing, so we can actually assess the effect of these variables over time on operational cost. Now let's take a look from a management perspective. In this example, we now want to compare operational costs across 4 plants. First of all, we look at daily production. If we know the total production cost, we can maximize production from the plants that are the cheapest to run, if they're serving a linked distribution system. This is not a static situation. One plant may be cheaper to run under certain conditions, but not others, so this type of dashboard facilitates real-time decision making. We can gain further insights by drilling into the data. So we start with total production costs here. This is power, chemicals, and sludge disposal. We can remove the power component of the cost and look at sludge disposal costs and chemical costs and compare the 4 plants. But we're still not really comparing apples with apples because these plants may be treating different source waters. So in order to compare apples with apples, we need to normalize for source water quality. Once we've done that, some interesting insights start to show themselves. In this example, plants A, C, and D are all treating similar river water qualities, and yet plant D is significantly higher. Now this suggests that there are some operating inefficiencies on plant D, and investigating those could potentially realize some operational savings. If you'd like to know more, drop us a line and ask for a demo.